This is number 3 AP review for curve sketching. This is non-calculator. Let f be the function given by natural log of x over x, where our domain is x is greater than 0 to the right of 0. The derivative is given by 1 minus natural log of x over x squared. Write the equation for the line tangent to the graph of f at x equals e squared. So anytime we want to look for tangent line equation, we're going to gather information about ordered pair, and then we can also gather information about slope, and then we can put it into point slope form. So we know the x value, so to find the y value we can take that e squared and put it into the original function. So natural log of e squared over e squared. We can clean this up a little bit. Anytime I have a natural log expression, I can bring that coefficient down in front, or bring this exponent down in front as a coefficient. So 2 natural log of e. Natural log of e is just 1. 1 times 2 is 2. 2 over e squared, that's just a number. So that's my y value. That's my ordered pair. To find my slope, I can take my x value, put it into my derivative equation. So 1 minus natural log of e squared over e squared quantity squared. Again, the exponent can come down in front because that's just part of a property that we can use for natural logs. 1 minus 2 natural log of e. Natural log of e is 1, so 1 minus 2 is negative 1. E squared, quantity squared, so the two exponents just multiplies together. We get e to the fourth. We get negative 1 over e to the fourth. So we have our ordered pair. We have our slope. And now we just put in the point slope form. So y minus y sub 1 is equal to the slope times x minus x sub 1. Part B, find the x-coordinate of the critical point of f. Determine whether this point is a relative max or relative min. So we have f prime. We don't have to find the derivative. We can just use what we are given here. But we're going to find critical points. So we're going to set f prime equal to 0. Meaning that if there is a numerator and denominator portion, we have to consider both the numerator and denominator separately, set both parts equal to 0, find our critical values, create our sign line, and then test our intervals. So if I set 1 minus natural log of x, the numerator of my f prime equal to 0, I get 1 minus natural log of x equal to 0. I subtract 1 from both sides, I get negative natural log of x equals negative 1. Divide both sides by negative 1, I get natural log of x equals 1. I can exponentiate both sides with base e. E to the natural log of x is equal to e to the first power. E to the natural log of x is just going to be x, so x is equal to e. And if I set the denominator equal to 0, I'll just get 0. And 0 just is a duplicate of my starting point. So my sign line starts at 0. My critical point is going to be at e. So now we have to test each interval. Between 0 and e, I can choose 1 because e is around 2.7. So if I plug 1 into the derivative function, I get 1 minus natural log of 1. That's 0, so 1 minus 0 over 1 squared. That's 1 over 1 is positive. So positive slope. And e is around 2.7, so I guess I could choose 3. But just so that we can make it easier, especially without a calculator, make it easier, we can match the form in terms of e. We know e squared is definitely larger than e. And if we plug e squared in for x, we'll have an easier time reducing, simplifying, and getting to our value within that interval. So if I put natural log of e squared in for x, or e squared in for x, natural log of e squared, I can bring that 2 down in front, so 1 minus 2 is negative 1. Negative over e squared, so negative over positive is negative. So we know that the graph is going to rise to some y value at x equals e, and it's going to fall after that. We know that therefore there must be a relative max at x equals e because f prime changes from positive to negative. Part C, the graph of f has exactly one point of inflection. Find the x-coordinate. So point of inflection means that we have to go one derivative level below f prime to get to f double prime. So this is set up in a form that's numerator divided by denominator. So I'm going to go through quotient rule. So here's my f function, there's my g function. So f prime times g minus f times g prime all over g squared. Distribute, combine like terms if I can, and I'm able to get it down to negative 3x plus 2x natural log of x. I can factor an x out, and x can be removed from the numerator and denominator, so this is my cleaned up version for my second derivative. I have negative 3 plus 2 natural log of x in the numerator, and the denominator I have x cubed. I'm going to set the numerator equal to 0 and also set the denominator equal to 0. So numerator equal to 0, I get negative 3 plus 2 natural log of x equals 0. Add 3 to both sides, divide by 2. Exponentiate both sides. We get x is equal to e to the 3 halves, so that's my critical point. If I set the denominator equal to 0, I'm going to get 0, and 0 is already a duplicate, so this is not going to be something that we're going to add in addition to our sign line. So the only critical point that is of concern for us is e to the 3 halves. We're going to test either side to see there's a change in sign. So I'll test 1 into f double prime. I get negative 3 plus 2 natural log of 1. That's going to be negative over a positive, which is negative. So I know that's the interval for must be second derivative value, which is concave down. E to the 3 halves is the critical point, so I'll choose a value that is in the form of e to make it easier to simplify. So I'll choose e squared. E squared is greater than e to the 1.5. So if I put e squared in for x, I get natural log of e squared. I can bring that 2 in front. Negative 3 plus 4 is positive. Positive over e squared. Positive over positive is positive, so concave up. So there must be a point of inflection at x equals e to the 3 halves, since f double prime changes signs. Part D. Find the limit as x approaches 0 from the right side of 0. So if we approach 0 from the right side of 0, the first thing we do is we plug 0 in, and we're going to get undefined over 0, and so we know the limit doesn't exist. But we can gather more information if we plug in a value, a decimal value like 0.1. So natural log of 0.1 is negative, 0.1 is positive, so negative over positive is negative. The behavior in terms of this portion of the graph, it's moving its way down to negative infinity. So technically the limit doesn't exist, but we can say negative infinity as the direction of the arrow moving towards 0 as it approaches 0.